So hello, this is part 2 of the series on questions on topic A4, rigid body mechanics. So today we'll look at some more in-depth examples. We'll do 5 questions just like in the previous video, and I'll do at least 1 or 2 more videos just like this, going through these typical exam style questions and the things to watch out for. So this first question, we have already a very common exam style questions where we have this ladder. It's a plank supported horizontally by this blue cable, and we have a wall on the left side. This is a fixed surface, and we need to calculate firstly the tension in the cable, and part B, the magnitude and the direction of the force exerted by the wall on the rod. So firstly, what we want to consider are the forces that are acting here and the direction they're acting in. So there's obviously going to be, just like in the previous video, if we have a uniform plank, uniform weight distribution, we always take the weight of the object in the center of mass of the object, in the middle. So this here we will take simply 58 newtons for the weight of the plank. We will have a tension force, which is going to be acting along the rope. Like this, tension always acts along the rope. We'll have this T, and we'll have some angle theta here. We will work with this. And then we have one more support here. So what we see is that this is a support that only allows rotation in this axis. It prevents the rod from moving up and down or left and right. It only allows it to rotate here. What that means is that we can have force components that are both horizontal and vertical inside of this support. So what we'll do is draw it like this. And the reason I know that it will be pointing in this way exactly is that we have rotational equilibrium. What that means is that if we take the torque about any point, it should be zero because the system is not rotating. So what we can do is consider our two forces that we have already given. If we extend these two forces over here and over here, then if we would write the torque about this point, we would also have to get zero, because if we write the torque about any point, it has to be zero. So that point included. What that means is that if this force from the support does not pass through this point, it means that it will have some torque, right? It will have this perpendicular distance and it will have a torque, and therefore the torque about that point won't be zero. So this force also has to pass through this point. So it has to point like this, such that its line goes through this point. Because then when we take torque about this point, all three forces will have a torque of zero because they pass through that axis of rotation. So that is how we know that the force from the wall will have to point in this way, like this. All right, so now that we have this, we can just label this like some force F, and then we can start writing up the equilibrium reactions. So we have translational equilibrium and rotational equilibrium. So that means that the rod is not moving in any way or rotating in any way. So what we can say is that the sum of the x component of the forces is zero, the sum of the y components of the forces is zero, and the torque about any point also has to be zero. These are our translational equilibrium, and this is our rotational equilibrium equation. So let's consider the x components of our forces. We have two x components. This force has an x component and this force has an x component. So we can say that Tx, the x component of the tension, or let's say Fx, is equal to Tx. There's nothing else providing a horizontal force here. So that will be for our x direction, and then for our y direction, we have Ty and Fy both pointing upwards. So the y component here and here, they both point upwards, and we have this downwards force of 58 newtons. So we have these equations here. And then we can also write a rotational equilibrium equation. So let's say, again, it's it's more, you always have to think a little about what point you want to take the torque about. You usually want to take the torque about a point that has as many forces passing through it as possible, because then you don't need to take the torque of those forces around the point, and so there's a lower chance of mistake, and it's just a quicker calculation in general. So let's say I want to take the torque about this pivot, because the distances will be kind of obvious. So there will be two forces with a torque, this 58 Newton force and this tension force. And more precisely, we could work with this sign to calculate this perpendicular distance here, although we don't need to, because we already know that this t is made up of two components, a y component and an x component, and we know that the x component passes through the pivot, and so it will not have a torque. So we only need to calculate with this y component, which we know its distance is simply 2 meters. So it will be very simple. So if we write the torque on the pivot, it has to be 0. And just like in the previous video, I'll take the torques that are rotating it counterclockwise is positive and clockwise is negative. So Ty will have an arm, or like a distance from the pivot, of 2 meters, and it's rotating anti-clockwise, and then we'll have a minus 58 times 1 meter, as it's in the center of the rod. So from this we can immediately calculate Ty. It's going to be 29 newtons. Now what we know is that you can use trigonometry here to describe Ty. If we just imagine Ty is over here, then we can see that the sine of theta is opposite over hypotenuse, so Ty over t, and so t is equal to Ty over the sine of this angle theta. However, we don't know what this theta is, so we still need to calculate it. So we know that this side is 3 meters, this side is 2 meters, and this angle is over here. So the tangent of this angle will be opposite over adjacent. So tan theta is opposite over adjacent, 3 over 2. From this we find that theta is 56.31 degrees. So we can plug that theta into here now, and we can find that the tension is 35 newtons. So this is part A. We have calculated the tension in the cable. And then for part B, we need to calculate the magnitude and the direction of this force exerted by the wall on the rod. So to do this, we have already written up the equations we need. We simply need to plug it in. So from this we can find Fy. We already know Ty. So Fy is simply 58 minus 35. So that will be, 58 minus 29. So that will be 29 newtons. And we know that Fx is equal to Tx from part A. And we can calculate Tx very easily. It's simply going to be the tension times the cosine of this angle. Again, we can consider trigonometry for this triangle over here. We know the angle, we know the tension, so we can simply plug those in, and we find it will be 19.33 newtons. So we know this is equal to Fx. So we know the x component, we know the y component, we need the force, so we can simply use Pythagoras to calculate the length of that final hypotenuse. So that'll be 29 squared plus 19.33 squared, which will give us approximately 35 newtons. So what we see is that indeed this force is going to be equal in magnitude to this force. So it is split equally, which means that the angle here is also going to be theta, 56 degrees. However, if you don't notice this, you can simply write up the equation for this small vector diagram, this force diagram, is that the tangent of theta is equal to the opposite force, so the y component over the x component, like this. And from this you will also find that theta is 56 degrees, or 56.31 degrees, just like for the other angle here. So this is a pretty common example. It's a good idea to be familiar with these, how we wrote up these equations, and well, from there it's pretty much just trigonometry and rearranging equations. All right, so question 7. We're given a cylinder of mass 5 kilograms and radius 0.2 meters. Is it attached to an axle parallel to its axis? So we have an axle over here through its center of mass, and we have a constant force. We need to find the angular speed of the cylinder after 5 seconds. So the way we can do this is that we know that there's going to be a torque acting for 5 seconds. Torque is the force, so we have this radius over here. So this force F has a torque around the pivot of force times R. Again, it's just the force times the perpendicular distance. We also know that torque is equal to the moment of inertia times the angular acceleration. Now we know for a cylinder, it's not given in this question. In IB questions it will be given, but for a cylinder the moment of inertia is simply 1/2 mr squared through this axis. So what we can do now is simply write that alpha is equal to 2F over mr. So we can simply plug everything in here. We know the force, 2 times 6.5 divided by 5 times 0.2. And so we can simply calculate this, and it will be 13 radians per second squared. This 2 came from the fact that we plugged this 1/2 mr squared into this and then multiplied over with the 1/2. All right, let's make this a big M. So now we have the angular acceleration. We know it was accelerating for 5 seconds, so we can simply use the fact that the final angular speed is equal to the initial angular speed plus the acceleration times the time. This is 0, so we have 13 times 5, which will give us 65 radians per second at the end of the motion. All right, so here we have a slightly more conceptual question, I would say. It is unlikely that IB will ask us to do something like this, although it is still very important to be familiar with the theory, because some of these concepts could be tested on the exam. So here we're given a point mass, a sphere, a cylinder, and a ring having a mass m and have the same radius r. The 4 bodies are released from the same position on an inclined plane. So what that means is we have some ramp like this, let's say, and they're all released. We have like a sphere, we have just a ring with a hole in the middle, we have a point mass, and we need to determine the order from the least to the greatest of their speeds when they reach level ground. Assume rolling without slipping. So let's just say that they all start from a height h. Let's say we have one of the objects here. Here they have potential energy, and they gain kinetic and rotational kinetic energy. So what that means is that usually in these kinematics questions, what we're used to from like previous simpler kinematics problems is that we only gain kinetic energy with linear speed. However, here at the end of the ramp, our ball will be rolling and moving forwards. So we will have kinetic and rotational energy, and due to we're not slipping, we don't have any losses, these two will be equal to each other. So we can say that the initial potential energy, which is simply mgh, is equal to the final kinetic energy plus the final rotational kinetic energy. So what we can use now is the fact that the angular speed of an object rotating is equal to its velocity divided by its radius. This is often a simplification we need to use when we write out these sorts of equations. So we can plug that in for here. So what we will have, I'll just write it up here. So we'll have mgh is equal to 1/2 mv squared plus 1/2 I times v squared over r squared. So what we can do on the right side is factor out a v squared. So we'll have v squared times 1 plus, and then we have the moment of inertia divided by mr squared. Yeah, well, if we could write this, well, I just start a new line, because what we can also do is divide down by an m to make it a little bit simpler, and we can also multiply over with these 1/2s, so that would be a little bit better. So if we multiply with these 1/2s, we have a 2gh, and we divide it down by an m everywhere. So now that if we factor out this v squared, we will have a 1 plus I over m r squared, because we divided by m on both sides. So now we can solve for the velocity. So we simply divide by this and take the square root. So we'll have this big square root here of 2gh divided by 1 plus I over mr squared. All right, so we have this general equation now, and the difference between the objects is going to be their moment of inertia. That's why their speeds will be different when they reach the ground. So this is the part where it's not really expected of us to know these different moment of inertias. However, it's important to have like a general understanding of like what moment of inertia has on the speed, the final speed. So let's consider the different objects we have. For sphere, we can say that the moment of inertia is equal to 2 over 5 mr squared. So what we can do is plug that into this moment of inertia here. So we will find that the speed is simply root 2gh divided by 1 plus 2 over 5 mr squared over mr squared. So this will simplify to a root 2gh times root 5 over 7, because these will cancel, and then we do 1 plus 2 over 5, 7 over 5. Since it's in the denominator, we can take the reciprocal. So we need to do the same for the other three objects. So for a cylinder, we know that I is equal to 1/2 mr squared. So we do the same little algebra, we just plug it in here, simplify out. We will find that the speed is root 2gh times root 2 over 3. And for a ring, we will have the moment of inertia simply being mr squared. So from this we find that the speed is equal to root 2gh times root 1 over 2. So we can simply compare these radicals. We know the square root is a increasing function, so if whatever is inside is larger, then the square root of it will also be larger. So what we will see is that the ring will have the smallest speed, as it has the smallest fraction in here. And then we have the cylinder, and then we have the V sphere. So what we notice here is that the ring has the largest moment of inertia, right? Because it doesn't have any of these fractions in front of it. So the largest moment of inertia corresponded to the slowest speed, and the reason is that the moment of inertia is this concept that is like a measure of like its resistance against motion, against rotational motion to be precise. It's like the equivalent of mass, only for rotation. The larger the moment of inertia, the more it's resisting rotation, and therefore it will reach a smaller final velocity. So this is just an interesting question, although this derivation here could be a good idea to at least understand the concept of it, because in these slope questions, in exam questions as well, you need to be able to consider these energy conservations and perhaps solving for one or two variables. All right, and in question 9, we're given a disk of mass 12 kilograms and radius 0.35 meters. So 0.35 meters. We're given is 12 kilograms. And we're also given the angular speed to be 45 radians per second. In part A, we need to determine how many revolutions, RPM, the disk is making. So we need to see how many revolutions it makes in 1 second. We know one revolution is 2 pi radians. So the number of revolutions it will make is 45 divided by 2 pi, like this. And if we want to convert this into minutes, this is only the number of revolutions it makes in 1 second. So we need to multiply by 60 so that we find it's 430 RPM. So this is how many rotations it makes in 1 second, and then we multiply by 60 because 1 minute has 60 seconds. And then part B, we're told a force is applied to the rim of the disk, tangential to the circumference. Determine the magnitude of this force if the disk is to stop spinning after 4 seconds. So we can calculate the angular acceleration simply from the fact that it has to be the rate of change of angular velocity over the rate of change of time. That's the definition of angular acceleration. We know it has to decrease by 45 in a time of 4 seconds. So the angular acceleration has to be 11.25 radians per second squared. Then we know that the torque, so if we apply some force here, the torque of this, as we've already seen previously, will simply be this force times the radius of the disk. And this will be equal to its moment of inertia times its acceleration. And we know it's a disk, so the moment of inertia will be 1/2 mr squared times alpha. But again, this would be given in the question. We are not expected to remember this. So here we can just rearrange for F. So we find it is 1/2 mr alpha. We can just plug everything in and find it 24 newtons. And then in part C, we need to calculate the number of revolutions it makes before stopping. So we again have to use the equation V omega final squared is equal to omega initial squared plus 2 times the angular acceleration times the displacement, which is in this case angle. So we can solve for theta. We know final speed is going to be 0. We know the initial speed, we know the acceleration. So we get 90 radians. But again, we need to calculate the number of revolutions. So we need to divide it by 2 pi. Because one revolution is 2 pi. This will give us approximately 14.3 revolutions. All right. And then question 10, the last one for this video. We have a uniform sphere rotating about a fixed horizontal axis through the edge of the sphere, so over here. The axis is at the height of the initial position of the sphere's center of mass, so over here. The moment of inertia of the sphere we're given. We need to find an expression for the initial angular acceleration of the sphere. So we know that at the start we have only the gravitational force acting here. It is creating this torque at a distance of r from the pivot, the radius of the sphere. So we know that the torque is going to be the moment of inertia times the acceleration. And so we know that the torque is going to be the weight times this radius. The weight is simply mg times r, and the moment of inertia we are given times our angular acceleration. So we can rearrange for our angular acceleration, and it will be simply 5g over 7r. And then part B, we need to state and explain whether the angular acceleration is constant in magnitude as the sphere rotates. And well, the answer is no, because for the angular acceleration to be constant, we need this distance here to be constant, right? So the moment, if we just consider this part of the equation here, if we want acceleration to be constant, then obviously moment of inertia is constant. We need the right side to be constant as well. Well, mg is constant. However, the radius won't be constant, because if we consider the sphere, this distance is always the perpendicular distance. If we consider some intermediate state where the sphere is like this will be the weight, and this will be the distance. Because we always need to consider the perpendicular distance, not this distance. This is not perpendicular to anything. We need to consider this perpendicular distance, and as we can imagine, when it reaches this point, it will actually have a torque of 0 because it will be passing straight through the axis. So we cannot state it has constant angular acceleration, and therefore we cannot use any of these Suvat equations, which all assume constant angular acceleration like these equations here, because our angular acceleration is not constant. So we cannot use any of these questions, and this does come up in exam questions as well. So yeah, so the radius is, or the distance is not constant, as I explained. And then in part C, we need to find an expression for the angular velocity of the sphere as it moves past position B. So again, we cannot use any of these motion equations, so we need to use energy conservation. So at the start, we have potential energy, and the potential energy can be described with simply, well, at the start, we have potential energy. Let's say that we have, well, mgr. If we take this height to be 0, then at the start we are at a height of 0, so we have mgr, and at the end we will only have rotational energy, so like this. And so what we need to rearrange for is omega, so we know the angle, we know the moment of inertia, mr squared times omega squared, and we just need to rearrange for omega from here. So we will find it as root 10g over 7r, like the r cancels out, the m cancels out, and then we can just rearrange to find this expression. So that was the last question for this video, and see you in the next one.